So now you can start your slides.
I have shared it. What should I do?
Sir, right now you are sharing your screen, sir. You can start your PowerPoint and that will be shared on the screen, sir. Yes, sir.
So my slides are visible.
Yes, sir. Your slides are visible.
So I just have to make it full screen, right?
Yeah, yes, sir.
Okay. Is it audible and visible? Everything fine?
Yes, sir. It's audible as well as visible, sir.
Okay. Okay. Good afternoon. I think it was supposed to be good morning, but now it's good afternoon to all. And also, I apologize to everyone for causing you trouble because my computer suddenly stopped functioning with the platform. So I was logged in, but suddenly I was logged out. So it took some time. So I really appreciate your patience to listen to me, even though I have caused nearly 45 minutes delay for everyone. And also, I like to congratulate the Government College of Engineering at Kalahandi for taking such an initiative to organize such an interesting event for the faculty development program on this interesting topic of modeling, simulation, and experiments with mechanical applications of this. So basically, and also in particular, I'd like to thank Dr. Raut and Dr. Apurva Das for remembering me and for considering me as a speaker in this field. You will notice that I am not belonging to mechanical engineering department. I belong to physics department. But before joining to NIT Durgapur, I used to work at MPA Switzerland for about 3 years as a scientist in the mechanical systems engineering department. So that is how I got connection with applications of physics in mechanical engineering. Okay. So as you can see, the title of my lecture, it says carbon nanostructures, reinforced lightweight polymer composites, an investigation into the filler matrix interface. So basically, I think I have seen last 10 minutes of the presentation of the previous speaker, Professor Panda, and I noticed that he also spoke a lot about carbon nanotubes and all. So this lecture is also going to be a lot of carbon nanotubes, but this will be entirely experiment. There is absolutely no modeling. So if you are expecting anything modeling, this lecture is not for you. I'm sorry for that. So let's move to the next slide. So basically, the outline of my slide. Before I go to the outline, those who don't know much about NIT Durgapur, perhaps many of you have visited NIT Durgapur campus. If you have not, then this is the snapshot of NIT Durgapur. It's founded in 1960 as a regional engineering college. In 2003, it was upgraded to National Institute of Technology as a deemed university. And 2007, it was declared as an institute of national importance by the government of India. So basically, since 2007, this institute really got a boost in terms of doing research and awarding degrees and etc. So now in 2020, we have different BTech programs, 9 BTech programs, about an intake of 800 students, 15 MTech programs with nearly 600 PhD students, and also MSc program in physics, chemistry, and maths. And from next year, also in life sciences. So we have nearly 210 faculty members right now. So those who aspire to communicate with NIT Durgapur, feel free to visit and contact the website to our faculty members. So this is the outline of my lecture. So the outline, basically, you see that at the start, I will briefly talk about what are the composites. So basically, this entire lecture is about composites. And so, but I think I expect many of you are already knowledgeable because it's a faculty developed program. So I think many of the people are faculty members who have studied composites. So maybe I can go fast also. If you feel bored, please give me some input. That it's you don't need to spend time for that. So then next I talk about introduction to carbon nanostructures, because my topic, my lecture will include both carbon nanotubes as well as some other carbon nanostructures such as graphene and graphene oxide and their derivatives. So I'll briefly introduce them. Challenges with filler matrix interfaces, brief challenges, briefly I'll discuss about them. Then I will have two full detailed experimental chapters or experimental sections on systematic investigation of filler matrix interface with carbon nanotubes as filler, and then another one on filler matrix interface with graphene oxide as filler. So two separate studies, one with CNT, one with GEO. Some conclusions and acknowledgement. So what are composites? If you read the textbooks, you will find that composites essentially are nothing but two or more dissimilar materials mixed together with a specific objective to enhance certain properties, right? So basically, you mix two different materials together in such a manner such that you expect that the overall property of the new material that you develop by mixing the two is increased to some at least for some property it should be increased. It can be mechanical, it can be electrical, it can be thermal, anything. But because we are talking about mechanical engineer, this event is for the mechanical engineering department. So our focus essentially is on the improvement of the mechanical properties. So when the focus is to improve the mechanical properties, then basically we normally have composites have two components. One is called the filler, and the other is called the matrix. So filler is the one that is usually has the superior properties in terms of mechanical, thermal, electrical, etc., which can be then introduced in a rather inferior property material that is called matrix, so that when you mix the filler into the matrix, the overall property of the matrix is enhanced by the good effects that the filler brings about into the matrix, right? So basically, there are always two components in a composite, where one is the filler and the other is the matrix. Matrix is usually the soft component, and filler is usually the harder or the stronger component. So in brief, you can. This is a cartoon I have copied from some net. I forgot to mention the source. I should have mentioned it. So probably in a rush. So basically, you see that if you imagine that your filler is like a rod or like a fiber, then you introduce this in a block of matrix, and then you develop a composite. And the composite, if you plot the tensile stress, this is the ideal case we are talking about, that if we consider the filler as a fiber, filler can be of different shape. It can be fiber, it can be particles. But if in this particular cartoon, the filler is like a fiber, so what we see is that the fiber has the highest tensile stress, whereas the resin, which is the matrix, has the lowest, and in between lies the composite tensile stress. Okay, so that is the idea, that you get development of the overall property of the resin by adding fiber. Now the question is, you can say that okay, fiber component has higher tensile stress, so why do you want to reduce the stress of the fiber? That's because you can't afford to make everything by fiber, and also fibers do not themselves bond together, so you can't make a structure just by fibers. You can imagine that in our house, in our buildings, we have concrete used for these making the pillars and the roof. So in the concrete, you must have noticed that we use iron rods. So, but can you think of that your pillar will be entirely made of iron rods? No, we don't, right? Because it will require a huge amount of iron. That will be much more costly. So that is the reason why we save the iron by using only a few number of rods in a mixture of concretes, right? So that is the idea of making a composite. So if you classify the composites into different types, you see, depending on the type of matrix, you can classify them into three types. There are ceramic matrix, polymer matrix, or metal matrix. And then in my lecture, because I am going to talk only about polymer matrix, I think the title of my lecture says lightweight composites. So lightweight composites you can only get by choosing the matrix to be a polymer, because metals and ceramics are much heavier compared to the mass of the polymers. The reason being, polymers are essentially made of carbon and hydrogen. I think you all know. So carbon and hydrogen being the lightest elements, if they make some compound, that compound is likely to be very light. So that is the reason why polymers are lightweight. So any composite that you make with the purpose of making it lightweight, you have to use polymers as the matrix. So this is the area that I will be talking about today. So that is why I focus on polymer matrix composites. So you see that polymer matrix composites have two types. One is the thermoplastic matrix composites, and the other one is the thermoset matrix composites. And you will notice that the later classification table, the bottom one, it says composite materials are classified into three types based on the reinforcement type. So what is reinforcement? Remember earlier I said that composite has two components. One is the filler and the other is the matrix. Now filler, when the purpose of a filler is to reinforce the mechanical properties of the composite, then the filler is often known as the reinforcement. So that is the reason the word reinforcement is more often used for the mechanical engineers. However, in other applications, if someone is making a polymer composite using some filler for the improvement of the electrical properties, it may not be you may not call it reinforcement. You may just call it a filler. But for mechanical engineers, reinforcement is the more common word because you essentially reinforce the mechanical properties. So they can be classified fiber reinforced, particle reinforced, structural composites in terms of laminates, right? So basically, you see then further classification of the composite can be made by dividing the fiber reinforced composites into thermoplastic matrix and thermoset matrix again. So again, you see there is a red circle or red oval surrounding the thermoset matrix composites. The reason being, my lecture will focus on thermoset matrix composites having fibers in it and also having particles in it. Okay, so having fibers in it as well as particles in it. So we'll see it later. And also on the right hand side, at the bottom right hand side, you will see I have circled laminated composites. I'll also talk briefly about laminated composites. Those who don't know what is laminated composites, I think I have one more slide at the next slide to explain it. So here you see that this is again a cartoon taken from net. So you see laminar composites at the top left corner. So laminar composite is the top left corner here. So what is this? You see that it is the kind of a sandwich actually. So you have one layer above of something else, one layer at the bottom of something else, and in between you have a dark color something else. So when you develop a composite by sandwiching one after one layer, if there are several such layers, then you call it a laminate. So these laminates are also of that. This is also essentially a composite because you are mixing, maybe not uniformly mixing, but it's a oriented mixing that you call, and you get a composite which is called laminar composite because the shape of the composite is kind of a lamina, right? And on the in the middle, you can also see fiber reinforced composites, where the dark circles essentially indicate the cross section of the long fibers. So several long fibers are introduced inside the block of the matrix. And here on the right hand side here, you see that a polymer composite is made of particles. So you have some white circles. So basically these circles or spheres are the particles that you have introduced inside the matrix. So similarly, you can see some more elaboration of the same thing at the bottom. So this is how different kinds of composites can be thought of. So lightweight composites are, as I have already discussed, that this is the area that I will be talking in my lecture. So you see, lightweight composites are essentially polymer matrix composites with because they have lightweight. Then my focus is thermosetting polymers because so I must tell you what is thermosetting polymers. There are two types of polymers usually available in the market. The polymers that we regularly use are the thermoplastic polymers because the moment somebody talks about polymer or plastic, it comes to our mind that plastic it must be very soft, it can be elongated, I can extend it, like pull it, I can make it thinner, I can make it thicker, I can melt it very easily. But all these properties are true only for thermoplastic polymers. These properties that we expect of a plastic are not entirely true for thermosets because thermosets are a special kind of polymers which are grown by cross-linking between two components. So that is what I have written in the lower portion. See, thermosets usually have two parts. It has resin and a hardener. So when the resin and the hardener are mixed in a specific weight volume ratio and heated at a specific temperature for a certain duration of time, they form hard plastics such as bakelite. Some of you might have heard the word bakelite. That is why I kept the name. So bakelites are basically black colored, plastics. Sometimes you might have seen the container of the batteries, car batteries, 12-volt batteries. These are often made of bakelite. There are many other applications of bakelite. Okay, so these containers appear to be very strong and hard. So, but they are not actually. So many may mistake that they are not plastics, but they are also plastics. But they are thermoplastic, thermosets. They are thermosetting polymers. The specialty of these is that once you give them a particular shape in a mold, you cannot melt them again. So that is the limitation of this kind of polymers. But the advantage is enormous. You see that mostly thermosetting polymers are epoxy resins, and these have superior thermal properties than thermoplastics. So basically, it means they melt at a higher temperature. Firstly, you cannot melt them, but if you want to degrade them or decompose them, they will decompose at a much higher temperature than the plastic, normal plastics, because normal thermoplastics start degrading any temperature above 100 degrees Celsius. But these thermoplastics, thermosets, will degrade at much higher temperature. A lot of times they can degrade well above 200 degrees Celsius. Epoxies are also widely used. Epoxies are actually widely used as matrix material for lightweight structural applications such as aerospace and automobiles. So these epoxy resins are the main component of matrix that are used for making composites for aerospace and automobiles applications. So you can see in this cartoon, there are several application areas mentioned for the epoxy resins. And you see it is the global market by 2021 is expected to be 8.77 billion. I have taken this from this source. So basically you see the can and coil coatings, automobile coatings, composites for the wind. Let's say there is a turbine, wind turbine needs a composite coating at the top to prevent it from the natural erosion, powder coatings, marine and PC, then adhesives, civil engineering structures, right? So these are the different shares, market shares, even electrical and electronics. So a lot of applications of these exist in the market for the thermoset resin composites. So there is definitely a scope to do research on these. So you see more animation coming. So the details are there. So, what are the prerequisites for a good filler? So, we have talked about the matrix, that is the thermosetting polymer. Prerequisite for a good filler is that the filler should be uniformly distributed within the matrix such that each of them are coated with the matrix, right? So, just because you have chosen a good filler which has extremely good mechanical properties, it doesn't mean that if you mix it in the concrete or in a matrix of polymer, it will give enhancement of the overall property. It doesn't happen like that. Why? Because the filler has to be uniformly distributed within the matrix such that each of them are actually coated by the matrix. Lot of time this doesn't happen and then you will not get the desired properties. The filler should also make a good interface with the matrix so that the load can be transferred easily and efficiently from the matrix to filler. Okay. So another aspect is not only the distribution of the filler into the matrix, but also the filler and the matrix in which it is put. They should interact. They should talk to each other. If they are staying together but having no interaction, then what happens when you apply a load? The load is applied perhaps on the matrix, but since the matrix is not weighting the filler, the load is not transferred to the filler. So better weighting of the matrix with the filler or the better weighting of the filler with the matrix is required. So that is what is the interface. The filler should also have very good chemical stability that it does not undergo any chemical changes as it is mixed within the matrix. And filler should have the large surface area. Additional, the last but not the least, the surface area of the filler should be very large so that it can only a small volume of it can cause a strong influence on the desired property enhancement of the composite. Okay, so that is actually the primary reason why we choose fillers in the form of small particles, fine fibers, fine flakes. No, we don't choose the filler as a bulk objects of big size, right? Fillers are always taken with a small size, and that's where comes the concept of nano filler, right? So why nano filler? Because nano filler has this advantage. There is a size effect of nano. If you see this cartoon, you see that if we have this block of the cube is a cube, and now you cut it into pieces. As you cut it into pieces, the volume of the cube doesn't change. If you add all the volumes of these individual 8 cubes, the volume will be the same. But what about the surface area? Surface area is significantly increasing, right, as you cut down. So that is basically means that if you choose a filler which is of small size, then it is likely to get more surface exposed to the matrix so that there is a possibility of better weighting of the filler surface with the matrix. So that is the reason that in the recent past, in the last 20, 30 years, most of the composite research has been focused to nano composite rather than just composite. And also it is partially to do with the discovery of several nanoparticles. The field of nanotechnology also evolved in the last 30 years than before. So in the last 30 years, as many and many new and new nanofillers came to existence, people became more interested in using the nanofillers into their research. So on the right hand side graph, it shows the same thing just in a different way. So you see on the left, on the x-axis, it is the particle size of a filler, and on the right, on the y-axis, it is the atoms in bulk to on the surface. So see, the bulk to surface number of atoms is increasing as the particle size is increasing, right? So as the particle size is smaller, the surface atoms compared to the bulk atom is increasing. So that is very important. If the surface atoms are increasing, if the surface atoms are increasing more and more, see here, so then what happens is that you see a large number of increase in the surface area of the particles, so that you get the higher probability of weighting of the filler with the matrix. Am I audible to everyone? Hello?
Yes, sir. Yes, sir.
Yes,
You're
okay.
audible.
Yeah, yeah. So introduction to carbon nanostructure. So because I have already spoken to you about that, that my topic is about carbon nanostructures, not just carbon nanotubes and fillers and graphene. So here, now that we know that there are some carbon nanostructures, this slide I really I'm fan of this slide. I made this slide back in 2005 or yeah, something like that, 2005, long back. But I still show this slide in every presentation that I make, because this slide shows carbon in nanoscale and in different dimensions. See, at the middle of the slide, you have the fullerene, which contains 60 carbons, and its size is only about zero point 0.4 nanometers. Its diameter is about 0.4 nanometers. So you can see that such a small particle contains 60 carbons, and that is why this can be thought of as if it's a quantum dot. It's a zero-dimensional particle. Okay. Now, if the fullerene is coated with multiple shells, if you imagine that you have one fullerene and then another sphere covering it, another sphere covering it, so it's a multi wall or multi surface fullerene. That is like basically a carbon nano onion. So this is the second slide. That is also kind of a quasi zero dimensional. This size is about 1 to 5 nanometers, and you can have multiple layers of carbon spheres, one in each other. That is carbon nano onions. Then on the next picture is of the carbon nanotubes, which is one dimensional because its length is in the order of several microns, but the diameter is only about few nanometers. So, and the bottom here, you see graphene. Graphene is what? Graphene is nothing but a carbon nanotube which is opened. So it's a flat surface where carbon atoms are sitting in a hexagonal manner, and then the first one is the nanodiamond. So diamond is a 3D structure, tetragonal structure, so tetrahedral structure. So this structure is diamond that can also be found in the nanoscale. So this nanodiamond, the another interesting thing is I have worked on all these materials till now. So I have published papers on fullerenes, I have published papers on nanodiamond, I have published papers on carbon nanoonions, I have published papers on CNT, carbon nanotubes, and now graphene. So what, how these things have evolved? That is the this slide. I am very interested to show those who don't know the history of carbon nanotube research or carbon nanostructure research. See, it started all in 1980 by the discovery of carbon nanotubes by Ijima, although it was not so well recognized. But 1985, C60 fullerene was discovered by Kroto et al., and they got the Nobel Prize in 1998 for this discovery. 1990, another discovery happened where fullerene synthesis was happened in the large scale. 1991 was major discovery again. Ijima discovered carbon nanotubes, single wall nanotubes. 1992, Daniel Ugarte discovered carbon nanoonions. 1993, again Ijima and Bethune independently discovered carbon nanotubes, single wall. Then 2002 is a big year for the research of carbon nanostructures, because in 2002 multi-wall carbon nanotubes were first grown by CVD method, which is the first step for popularizing the carbon nanotube research. Because earlier, carbon nanotubes used to be prepared by methods which would produce very small quantities. I remember my previous speaker was mentioning that carbon nanotubes are very costly, right? So I can tell you that when I started my PhD in 2002, my supervisor had bought 1 gram of carbon nanotube at a price of £1,000, which is like 100,000 Indian rupees. That is 1 lakh Indian rupees. 1 lakh Indian rupees for 1 gram. And he told me specifically that you can only spend, you cannot spend more than this 1 gram of carbon nanotubes for your entire PhD. That's all I give you. Don't waste it. That is all you can spend in the entire PhD. Now, in my group, I buy 1 kilogram of carbon nanotubes at a price of 40,000, 30,000 rupees. Okay, so 1 gram to 1 kilogram. See the difference in 20 years. So that is the major change that has occurred due to this discovery of 2002 that allowed people to produce carbon nanotubes in large quantities. Then 2004 is another major year because it is the year in which Gaim and Novoslev they first reported the individual isolation of single layer graphene, and 2010 was the major important year for popularization of graphene because it was this year that the discoverer of graphene were awarded the Nobel Prize in physics. And once you get a Nobel Prize in something, definitely the whole world looks at this material. So large attention grew from that onwards in the research of graphene. So this also happened with me because, as I said, in 2002, when CVD synthesis was reported, I started my PhD in that year. I also started to develop grow carbon nanotubes by CVD, and then I did a lot of research on carbon nanotubes. But in 2010, as I joined NIT Durgapur, as the Nobel Prize was awarded to graphene, I also started working on graphene, not leaving carbon nanotube behind, together with carbon nanotube, of course. So carbon nanotubes was there, but I also started working on graphene. So those are the works that. So to elaborate further, there are some cartoons, so you can see how carbon nanotubes are formed from graphene, right? So the animation is visible, I hope. So from the animation, it's evident that you can see that the cylinder is basically carbon nanotube, and once you open it, it is a graphene. I'm not going into the details of how you define a carbon nanotube. So here are another. If there are students as a participants, I think they will be very excited to know that how carbon nanotubes look like under a microscope because carbon nanotubes they are nano, so you cannot really see by eyes. So you need specialized eyes, which are essentially instrumental eyes. So we have several equipments in the last 20, 30 years which have been evolved. So one of the major discovery of an equipment is scanning tunneling microscope and scanning probe microscope. So these two microscopes were also discovered alongside with the discovery of fullerene in the year 1986. In fact, they also got the Nobel Prize soon after, I think, for the discovery of scanning probe microscopy, Gerd Binning and Rohrer. So on the right hand side, I have two images. One is taken by atomic force microscope of carbon nanotubes, which were grown by me. I grew these carbon nanotubes by myself in my own lab in the year 2003 in University of Nottingham using the CVD method. And then this is a scanning tunneling microscopy image of a single individual carbon nanotubes where you can see how the atoms are chirally oriented with an angle with the axis. Okay. Whereas the other two images are SEM images, scanning electron microscope images. The top one, top left, scanning electron microscope, where all the hair-like structures are essentially carbon nanotubes. And the second one is also a scanning electron microscopy image with a little high resolution. So those who are familiar, they're already. I think they might feel a little bored, but I think it's exciting. So again, the same I present here for the graphene. So what is graphene then? Graphene is essentially graphite. Graphite. We know that in a graphite is something where carbon exists in a flat structures, but there are several layers of flat sheets. In between the sheets, there is no addition. The only addition in between the sheets is the van der Waals force, which makes it easy for the layers to be separated. And that is how Gaim and Novoslev in 2004 they took a very interesting approach of using simply a Scotch tape, the double-sided adhesive tape, pressing it over the over a graphite, and then picking out a single layer of graphene, right? So how that graphene looks under the microscope? Again, this is a high resolution transmission electron microscope from which it was extracted. So this image is taken from Andreas Zettel group. This image, excellent image. You can see hexagonal structures. The yellow dots are essentially the carbon atoms sitting at each positions. So six carbons, one here, one here, one here, one here, one here, one here, right? So in each of them, you can see the hexagons. This is a real image taken by by the world's best high resolution transmission electron microscope. And this here in this diagram also you see a fine, you see a deep color of surface. This surface is nothing but a single layer of graphene floating or deposited on a silicon substrate. So this side is silicon. On the silicon, this is deposited a single layer of graphene, and that is imaged by a atomic force microscope. Here you see also the same thing, semi-transparent layer of graphene. When the graphene, you can isolate a single or two few layers of graphene, they are actually transparent. So you can see the semi-transparent nature of the graphene in the scanning electron microscopy image here. Okay. So why are these interesting? So interesting is because of these properties. See, graphene and carbon nanotubes both are very interesting for research because of the properties such as energy gap. Carbon nanotubes have an energy gap, and their energy gap is proportional, inversely proportional to their diameter, which means some carbon nanotubes can be insulator, some carbon nanotubes can be semi-metallic, some carbon nanotubes can be metallic, and some can be semiconductors. All depends on the diameter. So a material whose diameter will change its energy gap, the conducting properties. And for graphene, it's zero. For graphene, I'm sorry, I don't have a slide to show why graphene has a zero band gap. In the So graphene basically is a semi metal. So and that So electrical transport properties are also very good, because for carbon nanotubes, electrons can only travel along the direction of the tube. For graphene, carbon electrons can only travel along the surface of the sheet. There is no third dimension, so electrons cannot scatter on any other plane except the plane of the graphene. So that makes graphene and carbon nanotubes very good conductor. That is why they can also carry very large current density, 10 to the power 9 ampere per centimeter square. Diameter and length of CNT is about 100 nanometers maximum, and length can be up to 100 microns. Thickness and size of graphene. Graphene is very thin. Graphene has a thickness of 0.34 nanometers, and hundred of micron can be their size. Size can be hundreds of microns. So imagine if you have graphene, and if you want to mix graphene in a polymer matrix, the amount of area that it can be in contact with the matrix is enormous, because the thickness is so narrow, 0.34 nanometer, and the size can be 100 of microns. So one graphene sheet of 100 micron by 100 micron can can literally contact each and every molecule of the polymer, right? Because its thickness is just one atomic bond, 0.34 nanometers. Thermal conductivity is also very high, but the most important parameters are the bottom three parameters, which are important for reinforcing polymers, because these are the interesting properties that we desire in a good filler. So Young modulus of the graphene or carbon nanotubes are well above 1 terapascal. Tensile strength are also in the order of 200 to 300 GPa, gigapascal, and the density of the graphene or carbon nanotubes is within the value of 1.3 gram per cc. Let me tell you that the density of steel is about 8 gram per cc. So graphene has a density almost 6 times less than the steel, and the Young modulus almost 1,000 times more than steel. So that makes it very attractive as filler, and that is the reason why everyone wants to introduce graphene and carbon nanotubes in their composites for enhancing the property of the composite. But it's not that easy. So there are some challenges, of course, right? If it is not challenging, then there is no need for research. So the challenge is that graphene and CNT usually comes in highly entangled bundles. So especially for CNTs, because CNTs are hair-like structures, carbon nanotubes are hair-like structures. They
Hello.
easily form bundles, and once these bundles are formed, very,
Hello.
yes, yes.
Sorry to interrupt you, sir, but sir, our next speaker has joined, and
Okay. How much
uh,
time do I get?
sir, you can finish your presentation as early as possible, sir.
Can I take 15 minutes?
Okay, sir.
Okay, okay. So I'll go very fast then. Okay. So challenges in CNT and graphene is basically comes from the entanglement, also the insolubility in solvents, And inhomogeneous dispersion in polymers, they are not easy to disperse in polymers because they are basically inert. They don't have any chemical functional groups on them. So as a result, the bonding with the polymers is going to be very poor, very weak interfacial bonding. And small size also causes very difficulty in handling them. There is health hazard, so needs suitable chemical functionalization. So how to avoid these challenges, how to overcome these challenges is essentially by chemical functionalization. So it basically means you have to do some chemical treatment to the graphene or CNT such that they can be readily interacting with the matrix in which you want to put them, so that there is a good interaction, good adhesion between the polymer and the matrix, so that their properties can be instilled into the composite. Okay. So what is the knowledge? So lot of research is happening, but you will see in the literature lot of polymer composites that have been reinforced with graphene or CNT, they basically are based on thermosetting polymer. The reason is thermosetting polymers are very easy to improve. There is no cross linking, so they are more chain like molecules, so very flexible molecules. So if they are flexible, by adding some filler, you can control the flexibility. That is, you can improve the properties. But for thermosetting polymers, they are anyway quite hard. They are cross-linked, so it is not easy to improve them further unless you have really good property enhancement by good interfacial adhesion and good dispersion. So that is why we found that for the thermosetting polymer-based composites, the enhancement that have been reported are not great. They are within 30%, 50%, etc., etc. Not great. But in the thermoplastics, you will see 200, 500% improvement in the mechanical properties of polymer composites by including by incorporation of carbon nanotubes and graphene. So here I start my first part of the presentation, that is the carbon nanotube based interface investigation. So systematic investigation of filler matrix interface with carbon nanotubes as filler. So these are some materials that I have used. So some epoxy resin, the names and brands of the companies who produced it, the processing methods, how we produce the plates. On the top, you see the plate, and on the bottom picture, you see the laminates. I told you that we have also prepared laminates. So the photograph that I show here is a photograph of this is my own hand actually. I was making the laminate back in 2009 when I was working in Switzerland. So that is the hand you see. So these are the way. Details of the characterization methods. We have characterized it. So what are in the thing? I think I'm skipping these things. So I'm going straight to this part here. Yeah. So what is our approach? So what we did is to investigate in detail how the big question that we are trying to address was that in the literature, many people have reported that CNT can be introduced in the in the polymers to enhance their properties. But we were struggling. I have been working for nearly 1.5 years trying to get any improvement in the mechanical properties of the composite, in spite of adding carbon nanotubes. So it was really frustrating. What is going wrong? Every people are reporting, so many groups are reporting they are getting enhancement. So then what I did is I thought, okay, let me do a very bottom up approach. I study from bottom. So what we did is we used very small content of CNT, 0.28%, so that the CNTs themselves are not in contact with each other, and then we use them for dispersing in a epoxy resin. And then what we did is we simply used microscopic methods, that is optical microscopy, to study their dispersion properties. And here are the dispersion studies. So this work was published in 2011, and this work is highly cited. This is till now it is cited by 67 times. And this work basically shows that how difficult it is to disperse carbon nanotubes. So once you see in the slide A, it is a result of high shear mixer. We use high shear mixer to mix the carbon nanotubes in the polymer, and you see large chunks of dark particles. So these large chunks essentially means that carbon nanotubes are not well dispersed. There are regions where no carbon nanotubes. There are regions where are big chunks of carbon nanotubes. So we then also use another machine called high shear mixer plus ultrasonic bath to disperse them. Yes, this one looks very good, much better, not very good, better than this. Then the third one is ultrasonic probe. Ultrasonic probe is something that gives much more energy to disperse, mechanical disperse. So that is what is visible here. You can see that the dispersion of carbon nanotubes in this is better than the previous two, but it is still not good because we are still able to see dark particles. If you see dark particles under the microscope, the particles which are supposed to be nanoparticles, you are not supposed to see them at all in the microscale. The scale bar is only 100 micron. The fact that we are seeing it, that means there are still agglomerates. They are not nanoscale. These are agglomerates of particles which have micron size. So how to overcome that? What we did is we have also introduced another very costly method of mixing, that is a three-roll mill. This three-roll mill was purchased for specifically this particular project during my time in there. It cost, I think that time it was like 30, 40 lakhs of rupees. So that in the fourth slide, this slide here, you can see that there is absolutely no particles here. So this means, so this is the machine, three-roll mill, you can see. So this machine, if you pass through the mixture, then you get very good quality of dispersion. So now I was hoping that, okay, if I have a very good dispersion, then definitely my product will be very good. I will have improvement in the mechanical property. But when you tested the mechanical property, we still did not see any improvement. Why? So to investigate that, what we did is we have also chemically modified the surface of the CNTs. So first, you see this slide is without bike. Bike is basically a chemical modifier that is called dispersing agent, which helps to disperse the particles. So you see that some dark particles are there on the left hand side figure. The middle figure has no particles because we have used 1 weight% of bike. So basically we see that there is a strong influence of the bike, this BYK surfactant in improving the dispersion. And another try we did with a larger amount of bike, that is also very good, 8%. But we cannot use very much because this surfactant are basically soft materials. So if you use too much, they soften the material and your mechanical property will degrade rather than improve. So we also studied the influence over time. So immediately after preparation of the dispersion, and after you leave it for 16 hours. So what we observed is, you see after 16 hours, some dark particles appears. So this means if you mix them, it is not enough. You have to also maintain the dispersion. Mixing and maintaining are two separate things. You make a very good dispersion, but you have to withstand it for a long time. That is not happening because after 16 hours, we see some particles are being formed. Similarly, we have also studied the role of temperature. If you do it at room temperature immediately after preparation, and if you heat it at 80 degrees Celsius after 1 hour, you see some particle formation. Why we studied the influence of temperature? Because these resins have to be cured with a hardener at certain temperature. It can be 80 degree, it can be 120 degree for several hours. So we must ensure that if we have got a very good dispersion of the CNT in the matrix, the dispersion is stable over the entire process of curing for 6 hours or 8 hours at 120 degrees Celsius. If that is not happening, then we are unlikely to get any improvement. So that is actually what we found out, that after some time, if you heat, particles start to agglomerate. Another study, both the influence of temperature and time together. Again, you see, as we heat at 120 degrees Celsius, even at 5 minutes, we see some agglomerate formation. See, these black particles are agglomerating. But and even immediately after mixing at RT. So what is this? Is basically as soon as you add the hardener, there are two parts. Initially, you mix the resin, mix the nanoparticles in the resin. Then, after you have achieved very good dispersion, you have to add the hardener. So, hardener is a different chemical altogether. So, once you add the hardener, then again the system changes. The equilibrium of the dispersion of the particles changes. So, this is what we have seen, that even at immediately after mixing, as soon as you add the hardener, even at room temperature, the dispersion is changed. After 16 hours, it is even worse. See large chunks of materials and large regions where nothing is there. So this is slightly better, 80 degree, but this is again slightly worse because it is higher temperature. Why higher temperature is worse? Because as you heat, the resin viscosity lowers. So if the resin viscosity goes down, drops, what happens? The particles become more mobile and they can then go together and find together, make friends with themselves. So that's how they re-agglomerate the particles. So these are the challenges that one need to address. So further, was that, so this is again study by the adding of the hardener. As soon as you add the hardener, without hardener and with hardener. So and this was done with a modified, chemically modified aminated carbon nanotubes. NH2 groups were added to the carbon nanotubes. So these are the fracture surface of the plates that we have casted, and you see the fracture surface of this and that and that. You see with this one particularly, you see a lot of carbon nanotubes because it has 1 weight % carbon nanotubes. The others have very limited number of carbon nanotubes, but the breakage, what evidences is there is a pull out because you see the sharp edges, sharp white spots. Sharp white spots basically indicates that CNTs were also damaged. There are no large, long CNT particles. CNTs were long particles, long hairs were there, right? But here in the fracture surface, we do not see many long hairs. The reason is during the mixing process, we have also cut down the long hairs into very small particles. So the impact of fiber reinforcement has also been compromised. The fibers are no more fiber; they have been cut into smaller fiber-like particles, and that is also a problem which did not help in the cause of stopping the crack propagation or fiber pulling out. So I think I'll cut this. I'll skip this part because so this part again basically compares the storage modulus, and you see there is hardly any improvement in the properties, and the same applies here. No more improvement. So no properties have been improved. So in conclusion, we found that dispersion and the interaction is the most important, are the most important parameters before somebody can expect that there will be an improvement of the mechanical properties. Just mixing a good filler is not enough. How you mix, whether the mixing is stable over the entire curing process, is very important to determine the mechanical properties of the composite. We have also used the same concept in making a laminate. So basically, laminate is this. You see in brief, the problem of laminate is that the matrix is weak, but the laminates have usually fiber clothes, glass fiber reinforced clothes, and in several clothes are stacked together. In between, the matrix is introduced as a bonding material, but the matrix being very soft, you can improve the matrix properties by adding these hair-like structures, which are the carbon nanotubes. That was our idea. We did that, and by doing so, this is the slide again, how to make the laminates. This right-hand side bottom picture is the laminate making steps, and here we see some improvement. I am again skipping the these details. I'm going to the conclusion here. I think do I have the conclusion? Yeah. So the conclusion slide basically again in the laminate we see only 5% increase in the strain at maximum load, 13% increase in the flexural strength. In the tensile strength, we get only 5% increase, not even 13%, but at least in the bending mode, we get little extra improvement, but not much. So basically, there is problem of dispersion. Unless we settle the problem of good dispersion and good interface between the matrix and the polymer, matrix and the filler, this is not going to happen. So that is the reason why we chose in 2010, when we started the activity of the same activity with graphene, we decided instead of graphene, we shall first modify the graphene with some bond, chemical bond that will act or act very efficiently and interact very efficiently with the resin, because essentially most of the resins are cured with a amine based hardener. So we thought if the graphene can be modified chemically by a amine group, then the graphene as a filler itself will start acting like a hardener. So then it will be making very good bond with the resin. So with this motive in mind, we have developed a butyl amine functionalized graphene oxide. So these are the few steps that are shown how the graphene oxide was prepared, and from graphene oxide we prepared the amine functionalized graphene oxide. So amine functionalized graphene oxide has basically amine groups attached on the surface of the graphene. So this can be thought of as if like this. Schematically, this is like this. So you have the graphene oxide at the top, and after doing the butylamine treatment, refluxing, what you get is a graphene sheet, a graphene oxide sheet having areas where we have the butyl amine group. So this amine group essentially acts like the amine that is also present in the hardener, which is used for curing the resin. So that was the purpose of attaching the amine groups to the surface of the graphene oxide. And then we thought we'll conduct an investigation of interfacial addition of this butylamine modified graphene oxide with the epoxy resin system. So here are some characterizations. So this work was published in RSA Advances in 2016. So I'm skipping this part as well. I think for mechanical engineers, this is not important. What is important here is that we have been successful to produce a chemically modified graphene oxide into a amine modified graphene oxide. And we use this aminated graphene oxide. You can see this slide I like. I will spend a little time on here. So by adding the graphene oxide, by doing the chemical treatment, we have seen a significant improvement in the dispersion of the graphene oxide in various solvents. So that was an indicator that if we use this material instead of simple graphene oxide in epoxy, this material is likely to have better interaction. Okay, so and you can see on the right hand side the pictures after several weeks. So on the top, it is immediately after making them. At the bottom, it is after several weeks. And you see on the right hand side, the colors of the solutions are intact for many of the solvents. For example, for water, it is partially intact. For ethanol, it is not. For acetone, it is partially intact. For DMF, it is fully intact. For hexane, it is not. It is okay. For toluene, it is not. But here with geo, it is even worse. None of them are stable except this water, because geo is very stable dispersion in water. No other solvent keeps geo very well dispersed. So geo has a problem with dispersion except with water, but you cannot make a composite with water. Your composite will be made with some polymers, and good thing is that the modified geo is very good dispersing in DMF, dimethyl formamide. It is absolutely stable as well as in water. Okay, so that was the advantage. So and also you see this from the figures, you can see that the particle size. So I'll skip this. So let us go to the final discussion of how we have investigated the interface of graphene modified. So this is the investigation of the geofiller matrix interfacial interaction. So earlier I have presented how we have investigated the interface of carbon nanotube polymer composite. This topic now I am going to talk about how graphene oxide filler and the epoxy matrix interface was investigated by us. So these are the different steps of preparation of samples. So we used two sets of hardeners, one hardener that cures very fast, one hardener that cures very slow. And so this is the data of this G prime and G double prime. G prime and G double primes are nothing but the storage modulus and the loss modulus. And you can see that the values are at room temperature below 25 degrees, up to 25 degrees Celsius. The values, these blue values, are essentially increased. Excuse me. Hello. Went up. Okay. Okay. Sure. Okay. Okay, so since I have started very late and also I have taken a too long time, I think I'll have to cut this part short. So I'll go to the straight to the conclusion of this study. So conclusion of this study is here. So what we have observed is that even with the graphene oxide, the butylamine modified graphene oxide fillers were slightly better in terms of enhancing the interfacial interaction with the polymer, with the epoxy resin. However, since we have studied two separate systems, one with fast curing, one with slow curing, we found that the improvement of graphene oxide modified with amine group was more prominent with the slow curing system. So if you allow sufficient time for the reaction to occur, then you are likely to get more benefit of the interfacial interaction due to the chemical modification of the filler. Otherwise, even if you modify chemically the filler, the benefit is not visible if the system is very fast curing, because there is not enough time to act. Thermal stability of the composite are what is this? Nanocomposites is influenced both by the interfacial interaction. We have also found out that thermal stability is influenced by the interfacial interaction, and we have also seen that the fracture toughness is not only dependent on the interfacial interaction, but also internal stress development occurs. So this slide basically shows that internal stress can be generated in the opposite, which can oppose to each other, as a result of which, even though we have improvement in the interfacial addition, you do not always translate this into the improvement of mechanical properties. So, in short, the conclusion that we have found out in both the studies is that even if you modify the filler, even if you start with a extremely good filler having extremely good mechanical properties, there is no guarantee that experimentally the property of the material composite will be enhanced unless you are very very careful in modifying, in looking at the details of how fast they are curing, how well dispersed the system is, how the particles are well dispersed, how stable are the dispersion, etc. So I acknowledge my people who have contributed to this lecture. The manpower, basically, essentially, my two most important students, Miss Tia Klim, who is now an application scientist in Alstom AG in Baden, Switzerland, and Dr. Shobik Chakraborty. He did his PhD under my guidance. He is now a postdoc in Technical University Clausthal in Germany. And my collaborators mostly are my former collaborators and former who are from former employer, Professor Giovanni Terrassi, Dr. Michel Barbezat, Dr. Andreas Brunner, all from my former employer EMPA in Switzerland, and also collaborator Professor V.R. Dhanak from University of Liverpool, United Kingdom. Funding of this entire work mostly was done by the EMPA, that is my former employer and current collaborator, EMPA, Swiss Federal Laboratories for Material Science and Technology, and Indo-Swiss Joint Research Program. Thank you, and any questions, please?
Yes, sir. Any
Yes.
questions from the participants? Okay, thank you, sir, for delivering an outstanding and engaging session, which addressed excellent properties of carbon nanotubes, which makes it a desirable candidate in the various applications. We also got to know that these excellent mechanical properties of these nanotubes can only be exploited if they are properly dispersed.
Correct.
We hope that our participant will take the benefit out of this presentation and explore this emerging area. We truly appreciate and express our gratitude for your participation, sir.
My pleasure.
With this, we are moving on to next session.
Yeah, I understand. Because of me, everybody has suffered. So I am also really sorry for this.
Oh, sir,
No,
that
sir, not at
actually,
all.
sir, this thing happens. So thank you, sir, very much. You have spent the time with us, and we are fortunate that we have got you. And finally, your session is over. So, sir, thank you. I will talk with you later.
Sure, sure, sure.
Now it is over to Ankur.
Okay.
Please start the session 3.
So shall I unshare? I have to unshare my slide, right?
Okay.
Yes, sir.
How do I do that?
You
It's
can
already
stop
unshared,
sharing.
right? Yeah. I have to stop sharing, right? Yeah. It's done?
Yes, sir.
Okay.
Yes, sir. Yes, it is done.
Thank you.
Okay, so now I will introduce all of you to our next speaker, Dr. Ashok Kumar Mandal, sir. And before he starts his session, first of all, I will introduce him. Dr. Ashok Kumar Mandal is currently working as Assistant Professor in Mechanical Engineering Department in IIT Jamshedpur. Dr. Mandal got his BTech degree from Jalpaiguri Government Engineering College in the year 2007. Then ME in the specialization of machine design from IIEST Shibpur, Havra in the year 2009. He was awarded with PhD from IIT Kanpur in the year 2016. Dr. Mandal received approval for a project from DST costing 12.5 lakhs and CRG SERP project costing 65.5 lakh. Till now, Dr. Mandal has supervised 7 BTech projects, 2 MTech projects, and 2 MTech theses and 1 PhD. One PhD student is working under him. The research interest of Dr. Mandal includes dynamics and vibration, such as vibration of continuous system, non-linear vibration, acoustics of musical instruments, technology for rural development, etc. Now, I will ask Dr. Mandal sir to start his session.
First of all, thank you, sir, for this introduction and for inviting me. But please help me to share my
Yeah, definitely, sir.
presentation.
Sir, I've
Mhm.
made you the presenter. Now you
Yes.
can see at the bottom of the screen there is an arrow,
Right, right, right. I
share
can see
content.
that.
So, sir, you go through that arrow. You will see. Uh, okay.
Yes.
I think
Can
you
you
got.
see this?
It's
Is it
loading.
visible?
Yes, sir. Your screen is visible now.
Okay. Let me make it full screen. Is it fine?
Yes, sir. Now over to you, sir. Okay. Thank you, sir.
Okay. Thank you. Thank you. I welcome you all in this 1 week online faculty development program on modeling, simulation, and experimental approaches of mechanical systems. I'm really grateful, thankful to you guys for inviting me. I will talk about vibrations of strings in Indian plug string instruments. And let me tell you, this is part of my PhD thesis, which I did it in IIT Kanpur, and my supervisor is Professor Pankaj Wahi. So this is a part of my PhD thesis, and I'll be talking about this vibration of strings in Indian plug string instruments. So we are mechanical, most of us mechanical engineering background, and we deal with dynamical systems where mechanical vibrations are very important. But my interest here is vibrations of strings in musical instruments, and that too Indian musical instruments. And I choose one particular kind of Indian musical instrument, that is plucked string instruments. Now, there are three kinds of string instruments. One is called plucked string. That means you pluck the instrument to play it, and like sitar or sharod, this kind of instruments. The next kind of instrument is bowing string instrument like sarangi, sarinda, where you bow the string and play it. And then there is santur, which is a struck string instrument. We struck the string with a hammer, okay, or a set of string with a hammer. That is called struck string instrument. So there are three kinds of string instruments: pluck string instruments, struck string instrument, and bowing string instruments. We will be talking about pluck string instruments. So we will start our presentation with this. This is the outline of my presentation. First of all, we will talk about musical vibrations, what is called musical vibration. Then I will talk about very little bit about Indian plug string instruments. Then we will go for modeling it. In the beginning, we will talk about modal interaction in string modes when it is vibrating, and then mode locking, one phenomena will be describing, and then plate string interaction. So the actual instrument, the main source of vibration in a musical instrument is the string. We plug the string vibrates, and that vibration energy get transferred to the plate. Plate means the top on which the bridge is situated. We'll show you the figures, and the interaction between the string and that plate, that is the last part of our discussion. Okay, so first let us discuss this. What is called a musical sound? So first of all, if I say any sound you take, you just type here, there is a sound, and this sound is consist of many frequencies. And we are not saying that this sound is a musical sound. Why? Because it has many frequencies, and all the frequencies are not integral multiple of the fundamental. So there is a fundamental frequency, lowest natural frequency. If all the frequencies are integral multiple of the fundamental frequency, then only we say that this is a musical sound. Okay, so when we study vibration of string, we have seen that if there is some, so in the beginning of our study of vibration of string, this string is fixed at 2 points and it has no bending rigidity. Then all the frequencies, if you strike it, they'll have many frequencies. All the frequencies are integral multiple of the fundamental frequency. So here I have written natural frequency of a stiff string omega n. Omega n means n denotes any mode. So that mode's frequency is n into omega 0. If suppose this k is equals to 0, k is the flexural rigidity of the string. So for a string which is having flexural rigidity, means bending stiffness is there, then the frequency is represented, and natural frequency is represented by this formula omega n equals to n omega 0, this, where n is the mode number. So for, let's say, second natural frequency, so that's it, omega 2. Omega 2 is equals to 2 into omega 0. Omega 0 is the first natural frequency, and multiplied with this. So if k equals to 0, all the frequencies are integral multiple of the fundamental. And that sound is harmonic sound. That is called musical sound. Now if the stiffness comes, then what happens? All the frequencies, higher mode frequencies, become inharmonic. So when they become inharmonic, we will not say that the sound is musical. So now let's move on. Let's talk about, this is a book which was written by Swami Rama on Indian music, and he says that human brain can identify 66 frequencies in one octave, and among these 66 frequencies, 22 frequencies are musical, and we call them shrutis. In Indian classical music, there are 22 notes. They are called shrutis, and among them, in general, we know only 7 notes, sa re ga ma pa dha ni sa. Okay, and if you take the minor notes, that becomes 12 notes. Western music, you see, there are 12 notes in one octave. This is natural to us. Our brain can naturally identify these frequencies. But can you imagine? We cannot separate, if we have some sound, let's say sa re ga ma or a music, we cannot, in general, people cannot separate these sounds, which one is sa, which one is re, because we have untrained our brain. So musician, what they do, they train their brain, and they, so that they can identify these frequencies, and rare are those who can identify these 66 frequencies or these 22 musical frequencies. Now let's move on. The main inspiration of this work is coming from Sir C.V. Raman. Once he wrote, a fascinating field for research offers itself in the scientific study of numerous kinds of musical instruments found in India. Some of these instruments of indigenous origin are of undoubted antiquity and disclose a remarkable appreciation of acoustic principles. An investigation of their spatial features in comparison with those instruments of other countries may be expected to yield results of great interest. This is the main inspiration of our work. And yes, after our work, we found so many things which are really remarkable. And these contribution of Indian scientists thousands of years ago, what they contributed, and we are studying it in terms of modern science, and the some of the pictures you'll get in this work. So these are some plugged string instruments we found in Western countries. Purposefully, I have not shown you the the instrument called guitar, which is very much popular. Okay, here I am showing other instruments. These are all plugged string instruments, Western instruments. In the next slide, here I have collected some of the figures of Indian plug string instruments. These instruments, you can always compare the instruments of Western countries and instruments of Indian countries. These are all plug string instruments. The first instrument is called Sursingar. Here you can see there are no frets. You have to play it by rubbing against the steel board, rubbing your nail against the steel board. And the next one is Vichitravina. This instrument is played using a steel rod, which generally used in Hawaiian guitar also to change the effective length of the string. And this is called Swarbahar, Rudravina, and this is Veena. So all these instruments you can always compare. Their construction is very much complicated compared to the construction of these instruments. Now let us listen to this, to the sound of these instruments. The first instrument here we are showing, this is a tanpura, four string tanpura. There are four strings and no frets are there. Now how it, let's play the sound. One can see the richness of the sound. And let us play this sitar. So what is the difference of these sounds compared to the Western counterparts? The differences are, which are reported by several researchers, and one of them is obviously Sir C.V. Raman, who has reported it in 1921, and then other researchers. The main characteristics of these plug string instruments, especially sitar, the characteristics of the sound is this way. There are a large number of overtones. In one sound, let's say you strike it and you have one sound. In that sound, you have large number of overtones. And these overtones are less inharmonic. Less inharmonic. How it happens? Then the third is long sustenance of sound. Once you strike, the sound stays for long. Modulation of frequency. The frequencies which are present in that sound, these frequencies they have some modulation during time. As time goes, they have some modulation, and then amplitude also. Each frequency is having some amplitude, and that amplitude has some modulation throughout time. So our objective was to find out reason behind these characteristics. So we go for modeling this vibration of strings in sitar, veena, or tanpura. Now, before we go into that, let us again re-examine these facts. So first, here I play a sound of guitar. This is the sound of a guitar, and you can see the spectrogram here. What it is showing? It is showing how many frequencies are there in this sound and how the intensity of sound related to each frequency is changing with time. You can see that the first frequency here, the second frequency, third, fourth, fifth, sixth. How many frequencies are there? There are 6 significant frequencies only. And all those frequencies, how they are changing, their intensity of sound is changing. They are monotonically changing. So the sound is like that. Yes. I'm in a lecture. Can we talk later? Yes. Sorry, I thought the organizers were calling. So this is the first sound. Then let's play the second sound. This is the sound of a sitar. Okay. So this is the sound of a sitar. You can see the richness of this sound. Now, if we take the spectrogram of this sound, then you can see how many frequencies are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 frequencies are there. And the important thing is that you see the last frequency, 10th frequency. That is also a significant frequency. And how they are changing with time. Their change in time is not monotonic. They have some interaction. Some of the frequencies initially was not there, and then as time goes, they are coming. Some of the frequencies you see, they decay and then grow, they decay and then grow. Okay. Now let us go to another sound that is called Tanpura sound. And Tanpura is a very interesting thing where a cotton thread is used to give some richness to the sound. Without that cotton thread, you, the sound is like this. And when you do the FFT, you see there are many frequencies present, but the last few frequencies are not that much significant. But when you use that cotton thread, the sound is like this. And most interestingly, you see the first frequency, its intensity is very low, but the higher frequency, the which one is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15. The 15th frequency, you see, that is much more significant. So we want to know what is the reason behind it. So in this work, I'll be doing that. Again, the same sound, the sound of sitar and sound of guitar we have analyzed here, and you see when we do this amplitude, how the amplitude is changing with time for a guitar sound. This one is related to guitar, how the amplitude is changing with time. You see the amplitude is from here, it is decaying monotonically. There is no interaction between modes. But here you see for a sitar, all the modes, they initially see for example this frequency, initially it was not there, then it comes, then go down, and then again comes, okay, and go to some good significant amount. Another thing, when we do the FFT of this, and you if you plot it, the FFT, you can see that there is it is not just a peak, there it is a distribution. So that means there is some modulation in the frequency. So these are all experimental findings from the sounds of sitar and tanpura. Now, as mentioned by C.V. Raman, and we observe it that the bridge of this sitar is a flat bridge. This bridge, compared to the bridge of a guitar, you can see this guitar bridge. This is the bridge, end of the string. This bridge is a sharp edge. This is a point end bridge. But in case of sitar, you can see this bridge. This is a flat bridge, and from the side you can see that there is some curvature in the bridge. So I draw a picture of the same thing, and this is for a Tanpura bridge where this is the cotton thread which is adjusted for the sound we have already uh, heard right now. Now our work is to model the vibration of the string against this bridge, which was not there for the case of guitar. For the case of guitar, you see this is one end and this is another end. Both the ends are like pin ends, and we can study the vibration like vibration of strings between two fixed ends. But in this case, you see The vibration string is not vibrating. In this case, the string is not vibrating against two fixed points, but this end, at this end, you see when the string goes up, the end point of the string goes from this point to some other point. That means this is a moving boundary problem, and we have done a modeling uh, of this motion. So what we did, we consider there is a parabolic breeze here. This is a parabolic breeze, and the string, this is the string which is fixed at this point in the left end, and the right end it is fixed at this point. So when the string vibrates, what happens? It smoothly wraps around the bridge and unwrap around the bridge. During this motion, the boundary of the string that changes. Okay, so there are some assumption. There is another. There is assumption. Is this? So in our model, we consider that the bridge shape is a parabolic shape. Always in this parabolic shape, you can change the parameters and you can change the shape. So in general, this is a parabolic shape that we have considered here. And the next thing, we consider that the string wraps and unwraps around the bridge. This wrapping and unwrapping is a smooth. And the third assumption we have is the string remains tangent at the point of contact. So at this point, the string ends. This is called point of contact. At this point, the string is tangent to the bridge. It has to be tangent to the bridge. If it is not tangent to the bridge, suppose the slope of the bridge and the slope of the string has some difference. When it will have some difference, only when if there is some adhesive force working here, but there is no adhesive force working between the string and the bridge. So this assumption is justified that the string is at the point of contact, point of separation is tangent to the bridge. Now we derive the equation of motion, which is not a very simple wave equation. This is a complicated equation, and this is due to that wrapping and unwrapping phenomena, and it comes with another condition. So for a string, there are two boundary condition, two displacement condition at two ends, but it comes with another condition that is called slope continuity condition, and that condition we have written here. Now the boundary become a moving boundary problem. So what we did, we use a dynamic scaling, this kind of scaling where this gamma is the length, of this contact, means how much the string is in contact with the bridge. This is the gamma, and then we have non-dimensionalized it. So this is small gamma, and this scaling gives us, so we modify the boundary from a moving boundary to a fixed boundary by this scaling, and then we do the analysis. So then what we do, after modeling it, after getting the equation of motion, now we want to verify what is the natural frequency of the system. So what we did, we have linearized the system, and then we got the natural frequencies. Those natural frequencies which I have not mentioned here, we got the natural frequencies are still harmonic. Okay, they are, that means they are, all the frequencies are integral multiple of the fundamental. But the mode shape, when we plot the mode shape, here I plot the mode shape. I have written the equation for the function for the mode shape, and this is the mode shape. And then what we did, this distance, the modal point, this nodal points, this is a one node and this is another node. Obviously these two points are two nodes. What is the distance of this node from x equals to 0, and that is given by this. And when I got the expression for that, what we found that you can see that this is a constant, this is a constant, but this quantity depends on this beta n, which is the modal coordinate of the system, which changes with time. That means the node point, its distance from x equals to 0, that is always changing with time. That generally does not happen with simple string vibration. What happens in simple string vibration? The node points are always fixed. That is why they are called node points. But in this case, you can see the node points are not fixed, and a zoom figure of this in the right hand side, you can see where you can see that the green line which I have drawn is the static configuration of the string, whereas the dynamic configuration taken at different time steps, they are not crossing the static line at a point. That means the node point is moving through the length of the string. So what it facilitates? It facilitates the frequency of the sound that has some modulation. That modulation is due to this motion of the node point. Okay, then what we did, then we solve it numerically. The equation we have solved it numerically. We have given the equation we have solved for 3 modes, and we have given a initial condition, displacement initial condition to the first mode. That means we have excited only the first mode, and you can see the other modes are coming into the picture due to the nonlinear interaction between modes. So here you can see that how in the beginning we said that there are large number of overtones. How these large number of overtones come? So initially you strike the string, you give energy to some particular modes. So if the system is linear, the system should vibrate with those modes only. But this is not a linear system. This is a non-linear system, and there is some modal interaction between them. Due to that interaction, what happens? Other modes also comes, and that violates Young-Helmholtz law, which was first observed by C.V. Raman. He has observed is experimentally, and he has reported. Now you can see that the mechanism behind it, why this law is violated, and we have all the modes present in the system which are not initially excited. Okay, now in this case you see that we if you zoom it, any of the figures, if you zoom it, you see there is some oscillation. This oscillation is having some frequency, and the amplitude of this oscillation, you see the amplitude of the oscillation, it starts from 0, goes to some 0.5, and again goes to almost 0, and again it grows. Okay, so there is some dynamics there with the amplitude, modulation of the amplitude. Here we see the modulation of the amplitude, but now we want to study what is the dynamics of this modulation of amplitude. To do that, what we do, we use a method of multiple scale. We have 2 time scales. One is this real time scale, and another is a slew time scale. So we use, for small amplitude oscillations, we use method of multiple scales, and we get this slow flow equations. I am not saying that you should know about all these equations. Just for presentation, I am showing this. These are the slow flow equations which I got from the method of multiple scale analysis. And these amplitudes and the change of this amplitude, the dynamics which is shown here in this equation is the change of this amplitude with respect to this slow time, and these are the slow flow equations. And then we verified these slow flow equations. We have plotted this slow flow equations with this red line, and then the numerical solution of the actual equation with this another blue line. So And then we found that they are exactly matching. That means our slow flow equations are perfect. Okay, now what we do here, I have shown those slow flow equations only for two modes to simplify the system. And then what we did, we have converted this slow flow equations into polar coordinates, and we have written the same slow flow equation can be written. I'm not presenting here, these are there, in terms of r and phi. Okay, amplitude and phase. The slow flow equations can be written like that. Then what we found that the natural frequency of the system can be written like this. It has two parts. One is this n pi by square root of where 1 minus b is a constant, and n into pi where if you change n, this quantity changes. And you see, in the absence of this quantity, this natural frequencies are harmonic. That means integral multiple of the fundamental. But if this quantity is there, it may not be a harmonic quantity. Now we explore the condition for the system where this all the natural frequencies will become harmonic. The condition, that means the natural frequency will be harmonic if we can write the system like this. The natural frequency is like this, where you see we have written del phi and del t1 by n into del phi 1 del t1. Here I have written that if the system is like this, then all the natural frequencies are harmonic. Okay, now we will find out condition for this case. And again, we do a transformation of coordinate. We move from phi to theta. Okay, here in the next slide, I have presented three mode equations. Okay, and then we for solvability condition and for periodic solutions, we found that this condition has to be satisfied. This condition has to be satisfied. N square r square, n is the mode number, r is the amplitude of a particular mode. This summation has to be constant. Now let's see. Now what we did, we found the what energy related to a particular mode. Suppose there is a nth mode. For that nth mode, what is the energy of the system? And we found that this is the expression for the nth mode. Okay, with this is the natural frequency, and then we do this. We calculated this ratio. So what is the maximum energy, kinetic energy of a mode, and the ratio of what is the maximum kinetic energy of the first mode? That gives us, actually that gives us the energy ratio of energy between two modes, any two modes. And when we substituted this relation n square r square summation of that equals to constant, when we substituted that in this, we found this relation. Here you can see in this relation, this is n is the mode number multiplied with Rn by R1. And when we do the solution and plot this for various mode numbers, we found that this quantity 1 by n minus Rn by R1 equals to, it becomes 0 as we increase number of modes. That means in case of sitar, you see how many modes present there. We see there are 15 modes, 16 modes, and some researchers reported there are 30 modes. So we examine that situation with 30 mode, and we see that this quantity is approaching 0 with 30 modes. What is the meaning of that? Meaning of that is this quantity becomes 1. If this quantity is 0, this quantity becomes 1. That means the energy of nth mode and energy of the first mode becomes same. So this is a remarkable result we got from this model, that the energy of all the modes become equal. and we call it equipartition of energy. So that mechanism of a boundary obstacle facilitates this, that all the modes will have same energy. The energy get distributed to all the modes. This is really interesting. Now let us move to our next thing. So then what we did, we take a practical initial condition for the string. That means you, when you plug, the string shape is like a triangle. We keep that triangle shape, and we found that this the solution of the system, and this goes to a fixed point where this goes to a particular fixed point where energy get distributed to all the modes equally. So we get a result here that is called equipartition of energy. Now we move forward to, so another thing we must emphasize here, that this is a particular choice. This is a particular choice. We explored the condition of mode locking, and then we found that the solution naturally goes to that condition only, mode locking. So when modes get locked, what happens? All the higher order frequencies, those frequencies are locked with the first frequency, and obviously they will be harmonic. And we did the same analysis, taking into account the bending stiffness of the string, and we found the same thing, that the energy gets distributed and there is mode locking is there, so which makes the sound, which makes the sound of sitar harmonic. Now we move forward to another model. In this model, we consider the vibration of the plate. The string is fixed on the bridge. The bridge is mounted on the plate. Here, this is a parabolic bridge. This bridge is mounted on the top plate of the sitar. I want to go back to show which one is called top plate. This wooden structure is called tabli, which is called top plate of the instrument where the bridge is situated on it. This is called tabli. So what we are doing here in the new model, we are assuming that this plate is like a, this plate can be represented like a translational and torsional spring, because when the breeze is vibrating and it is situated on the top plate, so the top plate restricts its motion. What are the restrictions given by this top plate? Restrictions are rotation of the bridge and translational motion of the bridge. Now we are saying that these two motions are represented, the restrictions of these two motions are represented by two springs. Now if we can find out what is the stiffness of these two springs, then we can have a good model to study this, study the dynamics. So what we did in this model, we considered the top plate is a circular plate. Although you have seen the top plate is not a circular plate, to simplify it, we considered the top plate is a circular plate, and we found the what is the equivalent stiffness, torsional and translational stiffness of the plate. How we did that? So what we did for a circular plate, suppose there is a force acting here, and what is the displacement due to that force? The force is a dynamic force, because the string is vibrating, which is a dynamic situation where the vibration depends on the frequencies of the string. So we consider this as a forced vibration. So we, now here we consider there is a force acting which is a dynamic force, and due to that what is the displacement, and from that we found out what is the stiffness of this plate, dynamic stiffness of the plate. Similarly, what we did, we considered two forces, two equal and opposite forces are acting here at a very at a distance, and we took a limit that this distance becomes 0. Due to that, what is the moment acting here, and what is the rotational displacement of this that point. So from that, we found out what is the torsional stiffness of this plate. Using this to what we get when we use this and then analyze, then we found out that for a and here we vary the thickness of the plate, and we see the nature of the natural frequencies of the system. Here you see one very important thing, that we started with a thickness 0.0035. This is some non-dimensional thickness, and then we increase the thickness. So look at this frequency ratios, which will tell you whether this system is harmonic or not. These frequency ratios, here you see first, obviously, omega 0 by omega 0, omega 1 by omega 1 is 1. And you see the second, third, fourth frequencies are not exactly harmonic. There is some inharmonicity. But as we increase the thickness of the plate, second row, if we come here, you see the second frequency ratio become 1.99 something. So this goes down, and but you see the other frequencies are still above the whole number. And this way, what it facilitates, what does it mean? So this way, if we go on increasing the thickness, and we move to this place, and you see all the frequencies which are less than the natural frequency of the plate. Here you can see, in the first case, the first natural frequency is less than the first natural frequency of the plate. In the second case, second natural frequency is less than the first natural frequency of the plate. This way we increase, and we go up to this. For this, all the 5 natural frequencies are less than the first natural frequency of the plate. And what happens? This happens with the ratio of the frequencies. Here you see all the frequency ratios are just below the whole number. Now, what is the contribution of this phenomena? So if there is some bending stiffness, the bending stiffness increases the frequency ratio, and it makes the natural frequencies inharmonic. But this situation is just opposite to that. So what we are saying, that we can choose the thickness of the plate such that it can counter the effect of the bending stiffness. Now we move forward. So here we, for the same system, we change the position of the bridge, and we found that there is a particular position where the inharmonicity is minimum. We move to the next model. In this model, what we did, see, this is also vibration of string and plate, coupled vibration of string and plate. Here we are considering the plate has only one mode. Why we are considering that? Because the string cannot radiate much sound. Much of the sound is radiated by the plate, the structure of the instrument. But the string radiates very small sound, and this plate acts like a monopole. So what we did, we take the first mode of the plate. We assume that there is only one mode of the plate, and that mode, now we derive the equations of motion of the system for this, where the plate and string are vibrating. It's a coupled vibration, and they are vibrating. And what we found that as we play with the thickness of the plate, we see that you decrease the thickness of the plate, the velocity of the plate increases. Okay, for that means if the plate thickness is high, the velocity of the plate is very small. This is obvious. But there is but why we are saying looking for the velocity of the plate? Because the sound intensity is proportional to the velocity of the plate. So that is why we are looking for velocity here. And we here we see that then you change then we change the another parameter, that is the length of the bridge. Although here length of the bridge and this in this figure, the length of the bridge and the curvature of the bridge, they are interdependent. So you change b, the alpha is also changing, alpha is the curvature of the bridge is also changing, and that's showing this kind of nature. Not I'm skipping this. And in this figure you see we fix the curvature of the bridge, but we change the length of the bridge. And you see, when we change the length of the bridge is increased from 0.01 to 0.05, the velocity of the plate is also increased. So it shows the dependency of the velocity of the plate on the bridge length. Now here we'll fix the length of the bridge and change the curvature of the bridge. So red one is the largest curvature, and if we reduce the curvature, what happens? The velocity of the plate is reducing. Now we, in our model, we incorporate a new thing, that is the breeze is there, and in actual case the string is fixed here, and the other side the string is fixed on some that is called langot, which pass where the string pass over the bridge. We have incorporated that, and we found that the effect of this extended length of the string, this we are calling extended length, this length is x2, this length we are calling extended length. And we found here that the point bridge, the velocity of the plate related to point bridge, where there is no curvature of the bridge, uh, the velocity is very small. And as you change this x2 values, the velocity increases. So with this, what we found that this this extended bridge or the curved bridge facilitates large amount of energy transfer from string to the plate, which is not happening if the bridge is a pinpointed bridge. So this is our observation from our models. What we found? We found in the first result, what I have shown, that the node points move along the length of the string, which facilitates modulation in the frequency. The nonlinear modal interaction between in the modes, which facilitates the modulation of amplitude during its during the time. And then large number overtone, as we have already discussed, that since there is an interaction between all modes, so whatever mode which are absent in the beginning, they will come because there is interaction between modes. So that is why large number of overtones comes. And due to mode locking, the sound is less inharmonic, the sound is not inharmonic. And lastly, the last result we found that the carb bridge facilitate enhanced energy transfer. If the energy transferred to the plate is higher, then that will help the plate to vibrate long. Okay, so this is from my side, and if you have some question, you can ask.
Hello.
Yes.
Yes, sir. Any questions from the participants? Participants, any questions? Well, I think, sir, they are very hungry, so that's why they are not asking the questions.
No problem. If there are some question, you can they can communicate to me, at my mail ID. All these results are published in reputed journals. You can check from my web page.
Yes,
Okay,
sir,
thank
definitely,
you.
sir.
Thank you.
Thank you, sir, for such an interesting lecture. Where apart from mechanical engineering, we got to learn so much about Indian musical instruments as well.
Yes,
It was really a very nice presentation, sir.
thank you.
Thank you,
Thank
sir. So, uh, okay, sir. Now to talk to the participants. So, dear participants, I am sharing a feedback form with you. Please fill this feedback form before leaving the session. Thank you. Hello. Please fill this form before leaving the session. Okay.